The last thing we're going to talk about in this chapter is complex ion equilibrium. So a complex ion is a charged species. It's an ion. It contains a metal surrounded by ligands. Now, ligand is a fancy term that means molecules, mostly neutral molecules, that are associated with or attracted to the metal because of interactions between lone pairs of electrons and the metal's high charge, for example. Um, in general, ligands are going to be Lewis bases. So they're going to have a pair of electrons available to donate to the empty orbitals on the metal ion to form these bonds. Okay? So water will work because you have lone pairs on the oxygen. Ammonia will work, the lone pair on the nitrogen. Chloride has 4 lone pairs. Cyanide has some lone pairs on that nitrogen. Hydroxide has lone pairs on the oxygen. Those are all Lewis bases. They have lone pairs to donate. Coordination number is the number of ligands attached to this metal ion. Now, typically, complexes follow the familiar shapes that you would get in VSEPR theory, and the size of the ligand is going to determine how many can go on there, and their orientation will be, maybe tetrahedral or octahedral or trigonal bipyramidal, depending on how many are on there. So, in order to make a complex ion, you have to have pretty high concentration of ligand compared to the concentration of the metals. You have to have a lot of ligand molecules to occupy all the positions, all the spaces around the metal ion. So you got to have a pretty high concentration there. Ligands attach stepwise. That means one at a time. Okay, so silver ion will attract a nitrogen lone pair on ammonia and will attach to that ammonia. Now, ammonia is neutral, so it doesn't affect the charge on the silver. It's still a +1 ion, but it attaches one. Now, once there's one on there, the next ammonia can come in and make a doubly substituted ion, and so on and so forth. So we're going to make a complex ion using the silver ion, and we're going to attach to it this S2O3. Now, S2O3 is an ion, okay? It has a -2 charge, S2O3, 2 minus. So when I take a silver ion and I put this -2 ion attached to it, the overall charge is going to be -1. If I put another one on there, I've got another 2 minus charges, so it's going to be -3, right? So I'm going to create this complex ion, 2 of them actually. I'm going to take some silver ions from silver nitrate, and I'm going to put it into a solution that's very highly concentrated with sodium thiosulfate, S2O3, 2 minus ions. Sodium spectator doesn't really matter, okay? So I'm putting the silver ion from silver nitrate into a very high concentration of thiosulfate ions. So the first one is going to associate, and that has a K value of 7.4 times 10 to the 8th. And then once I have one on there, I can associate a second one on there, and that has a K value of 3.9 times 10 to the 4th. Okay? So what I want to do is, using that information, I want to figure out what's the concentration of silver ions, the monosubstituted silver thiosulfate, and the disubstituted silver thiosulfate. Okay? So I've got a very high concentration of the thiosulfate ion, and so because of that, I'm going to try to use up all the silver. All right? So my original number of millimoles of silver is volume times molarity, 0.150 millimoles. The initial concentration of S2O3, 2 minus, volume times molarity, 1,000 millimoles. Okay, and initially I don't have any of the second ion, the second complex ion. All of that silver is going to get used up. Only a tiny little bit of the S2O3 is going to get used up, so the concentration of that is hardly going to change. And a little bit of my disubstituted complex ion will be produced. So the concentration of S2O3, 2 minus at equilibrium, 1.0 times 10 to the 3rd millimoles over the new total volume of this. When I add these together, I added 150 and 200 milliliters of the two solutions, so 350 milliliters of my solution is 2.86 molar. The concentration of the disubstituted ion is at 0.150 millimoles, again divided by the 350 milliliters, or 4.29 times 10 to the -4th molar. So I've gotten concentration of the ligand, concentration of the dye-substituted ion right there. Now, to find the concentration of the other ions, I'm going to use a K expression for the second one. So the dye-substituted ion is on the left. That's a product. And that's formed from the monosubstituted ion plus the ligand. Those are on the right. Those are the reactants. So my K expression is product over reactants, as always. The K2 value is given. And so I can now plug in what I know. I know the concentration of the dye-substituted ion that I just figured out and of the ligand, 2.86 molar. And I know the K2 value. So I'm just going to literally solve by algebra for the concentration of the monosubstituted ion, AgS2O3 to the minus 1. Okay? I can do the same thing to find the silver ion concentration. Okay, I can use the same values, the value I just calculated for the concentration of the AgS2O3, which is now a product, and silver plus the ligand, the thiosulfate ligand, are the reactants. So those go on the bottom. And I already know my S2O3 concentration from the first problem, and I know now the concentration of the monosubstituted ion from the calculation I just did. And now I can solve for the silver ion concentration. So it's just using algebra at this point. Go back over this example. It's a classic example of complex ion equilibrium and calculations. And it's really not that difficult. It may seem a little confusing, but go back over it and look at these numbers and see. Most of it's algebra. There's not very much in the way of calculations. There's just a little bit of stoichiometry there to figure out the concentrations of all of the species in the solution. Not very much silver ion left over, obviously. Look at how small that is. Okay, but give it a try.